Shri Gurubhyo Namaha. Welcome to our online learning initiative Ekalaiva. We will discuss AC voltage applied to a capacitor. So now let us consider AC voltage applied to a capacitor. So this is a capacitor which is connected with AC source. So this is a AC source and capacitor. And we know that the AC source, the voltage is given by V is equal to Vm sin omega t. When a capacitor is connected to a voltage source in a DC circuit, current will flow for the short time required to charge the capacitor. As the charge accumulates on the capacitor plates, the voltage across them increases opposing the current. That is, a capacitor in a DC circuit will limit or oppose the current as it charges. So when the capacitor is fully charged, the current in the circuit falls to 0. But here, when the capacitor is connected to an AC source, it limits or regulates the current. Okay, so here we have connected the capacitor to an AC source. So it will limit or regulates the current but does not completely prevent the flow of charge. The capacitor is alternately charged and discharged as the current reverses each half cycle. So now first let us assume where Q be the charge on the capacitor at any time. Then the instantaneous voltage, so Q be the charge, at any time T, the instantaneous voltage V across the capacitor. Instantaneous voltage across the capacitor across the capacitor. So this is the instantaneous voltage V. Across the capacitor is V is equal to Q by C. You are familiar with this. V is equal to Q by C. Now once again we are going to apply Kirchhoff's loop rule here, children. So from Kirchhoff's loop rule, so from Kirchhoff's loop rule, the voltage across the source and the capacitor are equal, right? The voltage across the source and the capacitor are equal. So we are going to write Vm sin omega t is equal to Q by C. So in order to find the current, we are going to use the formula. Okay. So what is our aim? We want to find what is the current. So to find the current, we are going to use the relation I is equal to dq by dt. So from this, can you write Q is equal to, so from this above expression, we can also write Q is equal to what? C, okay, you can write it as Vm C sine omega t. Okay, so in order to find this, what are we supposed to do here? I is equal to d by dt of substitute for Q. Vm C sine omega t. So we are going to differentiate this. So when you differentiate it, you will get that actually when you differentiate the sine omega t with respect to time, you will get omega cos omega t. Am I right? Okay. So omega, already you have this c here. So omega c Vm cos omega t. Okay. So now here, instead of this cos omega t, we are going to substitute sin omega t plus pi by 2. Okay. Trigonometric relation. So can we consider this cos omega t is equal to sin omega t plus pi by 2. Okay. And this term omega c Bm will be taken as Im. Okay, so this relation becomes I is equal to this. I'll write here, children, omega c Vm sine omega t plus pi by 2 will be written as I is equal to Im sine omega t plus pi by 2. This Im will be, so we are going to write Im is equal to, okay, I'll write here itself. Im is equal to omega c Vm. Okay. And now, actually, this Im, which is nothing but amplitude of the oscillating current. Okay. So, this is the amplitude of oscillating current. So, and this Im can also be written as so Im is equal to B divided by 1 by omega c. So what is this quantity? This quantity 1 by omega c is analogous to the resistance. Okay, this 1 by omega c is analogous to the resistance. And this quantity, which is also called as capacitor reactance. Okay, so this 1 by omega C is nothing but what? Capacitive reactance. Okay, so this is capacitive reactance. So Xc is equal to 1 by omega C. So how can you write the amplitude of the current now? So this amplitude of the current, the amplitude of the current is Im is equal to Vm divided by Xc. Okay, Vm divided by Xc. In the case of resistor, this will be R. In the case of inductor, this is XL. But here it is Xc. When we connect only the resistance, then R. When you connect, that is purely inductive circuit, this will be XL, inductive reactance. Here it is capacitive reactance. Inductive reactance means XL is equal to omega L. Capacitive reactance is 1 by omega C. Now, let us see the phase relationship between voltage and current. We know that V is equal to Vm sine omega t, and we are already know this current I is equal to Im sine omega t plus pi by 2. So from these two equations, we can very well say that the current which is ahead of voltage by pi by 2. Okay, current is ahead of voltage by pi by 2. So here is the phasor diagram. Okay, so this is the phasor diagram for the purely capacitive circuit. So this diagram is a phasor diagram for a purely capacitive circuit. Okay, and this diagram which shows that is here voltage and current, and along the x-axis we have omega t. Okay, so this graph of voltage and current versus omega t. Okay, so now first let us consider this phasor diagram. So look at this diagram, children. So from this diagram we can very well say that is this is the phasor diagram at an instant t1. Okay, so this is the current. This part is the current part. Okay, so this is the current. So here you have current. So you know that current I is equal to Im sin omega t1 plus pi by 2, and here you have this is voltage. V is equal to Vm sin omega t. Okay, so the current phasor I is pi by 2 ahead of the voltage phasor as they rotate counterclockwise. Okay, so this is very, very important. I told you very clearly, children, what is the phase relationship between current and voltage in purely capacitive circuit. Current is ahead of voltage by pi by 2, or else you can say that voltage is lagging behind the current by pi by 2. Okay. So this is the most important part. Okay. So this phasor diagram is very, very important. And here we have drawn the graph, that is variation of, so this graph which gives variation of voltage and current with time. Okay, so because you have voltage and current here versus omega t. Okay, so you can see here, children, the current reaches. So this is the current, this dotted line is the current. So the current reaches the maximum value. So here is the maximum value, again here 0, here maximum in the reverse direction, again 0, and again here maximum. Okay, but look at the voltage. So when the current is here, voltage is 0. Okay, so you can very well say that the current reaches its maximum value earlier than the voltage by 1/4 of a period. Okay, so this is the phasor diagram and this is the variation of voltage and current with time. Now let us continue with this capacitive reactance, children. Okay, so already you are familiar with this. That is, this capacitive reactance is equal to, that is, what is this capacitive reactance? Capacitive reactance Xc is equal to 1 by omega c, and you are very familiar with that. Of this, the amplitude of the current Im is equal to Vm by Xc. Okay, so when you consider this equation, that is, let us start with this. Again, I am going to write here, children. Im is equal to, okay, I will write here, this Im is equal to V by 1 by omega c, 1 by omega c. Okay, so Im is equal to V divided by 1 by omega c. Now I am going to compare this equation with Ohm's law equation, because in Ohm's law equation we know that I is equal to V by R. Okay, so you can very well say that this 1 by omega c, which plays the same role in AC circuit as is played by the resistance R in DC circuit. So you can call this term as capacitive reactance. Already we have discussed about all these things. Am I right? So this 1 by omega c, which is analogous to the resistance. Okay, so we are going to write this is the capacitive reactance and all that. Okay, the capacitive reactance, which limits the amplitude of the current in a purely capacitive circuit in the same way as the resistance limits the current in a purely resistive circuit. So now can we define this capacitive reactance? Yes. So you can define this capacitive reactance as a opposition offered by a capacitor to the flow of alternating current through it. Okay. So and Xc is equal to 1 by omega c, and already you know that 1 by, what is this omega? 2 pi nu c. Okay, so I'll write the definition here, children. Capacitive reactance is defined as capacitive reactance is defined as opposition offered by a capacitor to the flow of of alternating current. Okay, so this is very important. Okay, so capacitive reactance is defined as opposition offered by a capacitor to the flow of alternating current. Okay, so actually you can see here, children, this if you consider C is constant, then if C is constant, then you can very well say that Xc is inversely proportional to frequency. Okay, Xc is inversely proportional to frequency. Okay, so for direct current, what is the frequency? For direct current, the frequency is 0. Then you can say that that is Xc, if it is inversely proportional to frequency, means for direct current this frequency is 0, right? Then Xc will become infinity. Okay, Xc will become infinity. So for direct current, for direct current, frequency is equal to 0. Therefore, Xc is equal to infinity. So a capacitor offers infinite opposition to the flow of direct current through it. And we can also say that a capacitor blocks DC. Okay, a capacitor blocks DC. Okay, and now let me draw the relation between capacitive reactance, that is Xc, and frequency. So the graph will be like this. Okay, so I told you that a capacitor blocks DC. The two plates of a capacitor have a perfect insulator between them in the form of a dielectric. When the two plates of the capacitor are connected to a source of DC supply, such as a battery, then momentarily the two plates will be charged with the potentials of the terminals of the battery. Thereafter, no current will ever flow in the circuit. Okay, so this is very important, children. A capacitor blocks DC. Okay, so this is the most important concept. Then, what is the unit of this capacitive reactance? What is the unit of resistance? Ohm. What is the unit of inductive reactance? Ohm. That is XL. And here, the unit of capacitive reactance is once again ohm. Okay, SI unit of Xc, capacitive reactance, is ohm. Now, again, here we are going to discuss power in a purely capacitive circuit. So, we are going to discuss about power in a purely capacitive circuit. In a purely capacitive circuit. Okay. What is the instantaneous power supplied to the capacity? So we'll start with this. Instantaneous power supplied to the capacitor is, so we know that power will be represented by PC. So here this is for capacitor, which is PL means power supplied to the inductor. Okay, so hope all of you remember that I into B. Hope you can write what is I. I am sine omega t plus pi by 2 because current is leading. And what about B? B into Bm sine omega t. Okay. So can you write this as power is equal to Im Bm. What is this sine omega t plus pi by 2? Can you recall? So sine omega t plus pi by 2, which is nothing but cos omega t. Okay, so can you write it as sine omega t cos omega t? Yes. So sine omega t cos omega t. So this sine omega t cos omega t can be written as sine 2 omega t by 2. Okay. So power is equal to Im Bm sine 2 omega t by 2. Okay. So as in the case of an inductor, what is the average power? 0 in the case of inductor. Similarly here also, what is the average power? I told you that how will you represent the average power? Bar. Okay. So this is equal to Im Bm by 2 sine 2 omega t again. So average power is equal to, you can write it as Im Bm by 2. Average value of sine 2 omega t is, you are familiar with that, 0. So the average power over a complete cycle becomes 0. Okay. So since the sine 2 omega t is 0 as in the case of pure inductor. Okay. So what is the average power over a complete cycle, which is equal to 0. To receive our online lessons, please press the subscribe button and you will receive the latest updates. Thank you, students.